this on. I now call to order the Society's 2,450th meeting in the 150th year since its founding on March 13, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Francisco Cordova. I am delighted that today's meeting is being held in person at the Cosmos Close, including a pre-lecture reception and dinner with our speaker, and that we are currently planning for the next meeting to be in person here at the club as well, with our speaker on December 17th, Sean Andrews of the Harvard-Smithsonian Observatory. Beyond that, we will take it one meeting at a time, although we hope to continue meeting in person regularly. All in-person meetings will adhere to the COVID-related rules of the District of Columbia and the Cosmos Club. Proof of vaccination, including a picture ID, will be required for in-person attendance. Masking is strongly suggested, and we also suggest getting tested for COVID infection within 48 hours of the event. These requirements are subject to change with changes in the COVID-related rules of the District of Columbia and the Cosmos Club. So please check the PSW website often for up-to-date information. Of course, we will continue to live stream the lecture proceedings to YouTube for our remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the live stream recordings will be posted to the PSW YouTube and Vimeo channels, where they will be permanently available for everyone to view without charge. The Society is grateful to the sponsors of the 2021 and 2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. I am pleased to announce the following new members. Eswara Raju, an engineer with the Virginia State Corporation Commission, broadly interested in science and engineering, who learned of PSW on the internet, and Francisco Cordova, tonight's speaker, whose interests will be clear to you in some small part from tonight's proceedings. We welcome them to membership. If you are not a member and would like to join PSW or support the Society, you can do so through the PSW website, using the blue Join button on the upper right-hand corner of the home page. We welcome new members and we appreciate donations. www.pswscience.org. Recording Secretary James Hewlin will now read the minutes of the 2,449th meeting and the lecture by Robert Beyer on microchip accelerators, laser-driven particle accelerators on a silicon chip.
The 49th meeting of the Society to order at 8:04 p.m. Eastern Standard Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Robert Beyer, the Keenan Professor of Applied Physics at Stanford University. His lecture was titled, microchip accelerators, laser-driven particle accelerator on a silicon chip. Bayer's collaborative work with Peter Hammelhoff recently received the 2021 Leibinger Laser Prize for Innovative Technology in Europe. The two are working to miniaturize particle accelerators from many kilometers long to centimeters short. An etched tip of silicon will provide the source of electrons, which are pre-accelerated in a buncher and then are efficiently accelerated with a laser radiation to the requisite speeds. Bayer aspires to develop accelerators so small they, for example, could be implanted directly into the body to apply radiation directly to a tumor. Bayer summarized the historical context for his work. When he arrived at Stanford in 1955, the Stanford Linear Accelerator Center, or SLAC, was still under construction. The $100 million project took 10 years to come to fruition, led to multiple Nobel Prizes, and for its first 50 years, was the centerpiece of the particle physics community. In 2009, the world's first coherent X-ray laser opened at SLAC, bringing laser-like radiation into the X-ray spectral range. Bayer then described the history of his own work on introducing lasers to particle acceleration. His own work began in 1974 and took 30 years to produce its first successful experiment. In 2011, DARPA agreed to fund Bayer's X-ray generation program for 5 years, with the goal of showing a path to a portable X-ray source for medical applications in the field. He then also set to work on different kinds of accelerators. The SLAC accelerator typically runs at 30 megavolts per meter and approximately 3 kilometers to reach 10 gigavolts of electron energy. Bayer believes he can create an accelerator that does the same in the length of only 1 meter. Using a Ti sapphire laser to test damage thresholds, Bayer's team determined that fused silica and silicone are optimal building materials. They developed a bonded structure through which electrons travel and use a magnet to measure the electron energy. The experiments were challenging because the electrons came in 30-micron bunches and they needed to travel down a 0.5-micron channel. The team achieved its first success in 2013. Around that same time, Peter Hammelhoff achieved success in related research. Shortly thereafter, DARPA canceled Bayer's funding. The Moore Foundation filled the void and funded Bayer and Hammelhoff as an international collaboration dubbed the Accelerator on a Chip International Program, or ACHIP. Their goal was to demonstrate a shoebox-sized 1 mega-electron-volt accelerator and transverse effects. ACHIP started out by seeking to build all accelerator components to be compatible with planar lithographic processing, centered around the fused silica structure previously developed by Edgar Peralta. They began using tungsten tips as their electron source, before ultimately deciding that silicon nanotips were the most efficient. Those tips feed electrons through silicon dual pillar structures and are accelerated by Ti sapphire lasers. ACHIP is able to focus the lasers by changing their phases to rotate the acceleration gradient and to change the shape of the teeth of the gradient. The team then developed a tree branch structure to feed incoming laser light down to stay synchronous with the electron bunch. Bayer then described inverse design. He was surprised by this method, which allows computers to test a multitude of different designs subject to the same boundary conditions. His team used this method to design a microchip accelerator on silicon. Rather than rectilinear, the resulting design is an object full of what Bayer called funny shapes. In January 2020, Bayer's team published in Science the world's first on-chip integrated laser-driven particle accelerator. ACHIP is now in its 7th year and had 36 publications last year. They are now working to focus electrons going down the accelerator and to make their currently shoebox-sized accelerator reliable. The speaker then answered questions from the online viewing audience and from those present in the room. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:37 p.m. The temperature in Washington, D.C., 5 degrees Celsius. The weather, clear. Number of in-person attendees, 32, and concurrent viewers on the YouTube live stream, 25. Total views on the PSW Science YouTube and Vimeo channels, 476. Respectfully submitted, James Heelan, Recording Secretary.
I have the president's microphone. Thank you, James. Are there any comments on the minutes? Online listeners, please enter your comments in the YouTube chat box. Otherwise, send comments to corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. Hearing no comments on the minutes, I will entertain a motion to accept the minutes as read. I'd have a second. All members in favor of accepting the minutes as read, please raise your hand. All those opposed? Hearing no opposition, the minutes are accepted unanimously as read and will be posted to the website in due course. We now turn to tonight's lecture, the Arecibo Observatory, Legacy and Ideas for the Future. It is my pleasure to introduce tonight's speaker, Francisco Cordova. Francisco is the director of the Arecibo Observatory, for many years home to the largest single dish radio telescope in the world. Previously, he served as senior manager for composite materials and fabrication for Boeing Research and Technology. As observatory director, Francisco has overall responsibility for the observatory's research portfolio, for developing the facility's budget, and for the engineering activities and facility operations carried out by over 130 scientists, engineers, and staff members at the observatory. He is the youngest director ever to lead a large facility for the National Science Foundation, and he is now deeply involved in planning the observatory's next stage and securing the support required to realize it. Francisco earned a BS in Civil Engineering from the University of Puerto Rico at Mayagüez, and an MS in Civil Engineering from the University of Michigan, Ann Arbor, and he is a registered professional engineer. All questions will be fielded during the Q&A session after the lecture. Francisco, the stage is yours.
Thank you, Larry. Really appreciate the opportunity to be here today. And as Larry mentioned, my name is Francisco, and I'm the director for the Arecibo Observatory. Today we're going to talk about a couple of different things. And this is going to be a pretty dynamic presentation because it'll encompass a lot. We're going to talk first about the facility overview, right? What is Arecibo? Why is it important? What has it accomplished in the past? We're also going to talk about the collapse of the 305-meter telescope, which happened in December 2020, and how that has changed the observatory, right? It has changed short-term goals. It has changed visions for the future. And so we're going to go into a little bit of detail on that. Then we're going to talk about the recovery, right? What has been the actions that I've been taking after the collapse has happened, and then we move into thinking a little bit more creatively about what's in the art of the future, what have been some of the ideas that are already taking shape to form the future of the facility, and others that may be more long-term than immediate solutions for the facility. And so the Arecibo Observatory is really a multidisciplinary research facility that focuses in science in three different fields: radio astronomy, space and atmospheric sciences, and planetary sciences. The facility is a facility of the National Science Foundation as part of their large facilities portfolio, and it is located, as the name says, in Arecibo, Puerto Rico. Originally built in 1963 by ARPA, or the predecessor to DARPA. At that time it was the Advanced Research Projects Agency. It was initially intended to really study the ionosphere and help us gain some understanding of the space. Remember, we were out in the space age back then, or the space race. Sputnik has just gone into orbit, and we were really trying to understand what had gone into orbit and how could we control the ionosphere or understand the ionosphere a little bit better. Okay. Until recently, the facility hosted the largest single-dish radio telescope in the world until its collapse in 2020. And even though it has was built in 1963. It went through several rounds of upgrades, and we're going to talk about those a little bit in a couple of minutes here. But in addition to the research facility itself, it also has a lot of other assets or values in the same site. And so we have a visitor center that typically receives over 100,000 visitors in any given year. We also have restaurants and cafeterias. We also have a hotel on site that is available for both the science personnel that comes to use the telescope, as well as visitors that just want the experience to stay at the observatory. Okay, so on any given day, it's a pretty dynamic environment at the facility. This picture gives you an idea of just the layout of the 118-acre site. And so here you have, of course, what was the crown jewel of the facility, the 305-meter telescope. This is the telescope platform here. That was a suspended platform held into place by suspension cables. Here you have your visitor center or museum, and so if you were to visit the facility, this is kind of where you would access it. And these are the towers, right? So the platform itself, the platform telescope, was suspended by 3 main towers, and they're named Tower number 12, Tower number 4, and Tower number 8 in the back there. You can barely see it on this one. We also have several other laboratories and facilities on the site, and that includes an optical lab, a LiDAR lab, and then also the heating facility, which is right in the middle of the dish. You can't really see it in this picture, but you'll see it in once in the future. And so, of course, we have our warehouse, our engineering, and our maintenance areas right here. And so the operating model for this facility is really managed by a cooperative support agreement. And the University of Central Florida has the main award for the management operations of the Arecibo Observatory site. So we do that in conjunction with 2 other team members, and that is Yang Enterprises and Universidad Ana Jiménez. So while UCF has main responsibility for operations of the site and all of the science and research aspects of things, Yang Enterprises manages engineering and maintenance, and then Universidad Ana Jiménez, who is a local university in Puerto Rico, manages the education and public outreach components of the facility. Okay. This has been what typically has been the financial profile for Arecibo. Okay, so we get funding from 3 main sources. NSF foots the majority of the bill with a contribution of about $7 million a year. NASA funds the Near-Earth Object Program as part of their planetary defense program for studying asteroids, near-Earth objects, and helping us characterize those, including predicting orbits into the future. And so that's at about $4 million a year. And then there's about $500,000 that comes in from the sale of observation time to other entities, either private corporations that are interested in using the capabilities or other DoD applications that also pay for specific usage of the facility. And so this kind of gives you an idea of what the legacy capabilities were surrounding the 305-meter telescope itself. Okay, so some of the main things were the radar capabilities. Okay, so we had 2 radars, one a 430 megahertz incoherent scatter radar that was 2 megawatts in power, the most powerful and sensitive incoherent scatter radar in the world, used for atmospheric studies and understanding the ionosphere. We also had a 1 megawatt S-band transmitter, which was the most powerful planetary radar in the world and helped us understand near-Earth objects a lot better, helped us also map the surface of planets. We had an ionospheric heating facility that had 2 different frequencies, one at 5 megahertz and the other one at 8 megahertz. And we also had a suite of GPS receivers, digital ionoson VLF receivers, and then your regular astronomy receivers. These are kind of your bands for our receivers. We would go from about 327 megahertz all the way up to right at 10 gigahertz. Okay, and so that's kind of the field for Arecibo. 327 up to 10. Above 10, the surface of the primary reflector was really not good enough to go above 10 gigahertz, and that's why it was really kept at that cap. If you really wanted to go, let's say you wanted to do 12 or 15 gigahertz, you would have had to resurface the primary reflector, which is no easy feat. And so Arecibo has had some pretty significant historical accomplishments throughout its 55-plus year history. And so starting with the determining the rotation rate of Mercury and also discovering the first pulsar in a binary system. That actually led to a Nobel Prize. We also had the first radar ranging to an Earth-crossing asteroid and the discovery of millisecond pulsars. Okay, so this all happened between the 60s and the 80s for what was considered kind of the glory days of the Arecibo Observatory, right after it had passed from the Department of Defense over to the National Science Foundation for science operations instead for military applications. And so then in the 90s, it really kind of focused more on long-term data trends of studying the ionosphere and providing mission support. So when SOHO spacecraft at some point was lost, it was the Arecibo radar that was able to ping it and identify its location. In the 90s as well, we had big discoveries by discovering our first exoplanet. The first exoplanet ever was discovered at the Arecibo Observatory. Now we have over 4,000 of those exoplanets, and we continue to discover more every week. Then in the 2000s, really more focused on the planetary radar capabilities. Of course, we continued our studies of pulsars and nanograv, gravitational waves for radio astronomy. But a lot of the time spent over the last 20 years was really supporting the near-Earth objects observations that were part of the planetary defense program for NASA. And in addition to all the scientific accomplishments, Arecibo is really a STEM education powerhouse for Puerto Rico and for the world. And so over 375 doctoral dissertations, over 2,000 peer-reviewed publications coming out of data used by the, data produced from the facility itself. We have typically about 150 users every year from 100 institutions and broad government support. So we have users from the National Science Foundation, from NOAA, from NSF, from NASA, from DOD, right, AFRL, NRL, a lot of really broad support and interest from the general. And in addition, student engagement is very significant. And so the student programs at Arecibo range from high school programs all the way to postdoctoral researchers. And so right now, we've had about 1,100 students in observatory programs, and those includes both the Star Academy, which is a high school program. We take 60 students every year, so 30 per semester. And that particular program, which is sponsored by NASA, has a 97% rate for those students graduating from a STEM field, okay? So 97% success rate of the folks that go into that program, so it's amazing. In addition, of course, we were really an icon, right? It's the largest radio telescope in the world. Over 600,000 students visit the facility in its lifetime, and over 1.5 million visitors as well. And so it was really one of these places where you go as a kid. I mean, I grew up in Puerto Rico. I remember going there on a field trip when I was probably 9 or 10, because that's one of the things you would do, right? You would go to the radio telescope. That was one of the mandatory field trips. And it was one of the amazing things of having that telescope there, the fact that you could so easily visit it and get inspired by the great science that was done there. And if you didn't understand the science, because at that age, maybe you didn't as well, you were marveled at the engineering and at the magnitude of the telescope that you were looking at. And so the facility has really evolved over the years. And so in 1974, a new surface was actually placed that would enable better observations of the ionosphere and also enable way better sensitivity for radio astronomy applications. From there in 1991, a new Gregorian system was installed, which further increased the capability for us to have multiple receivers on almost simultaneously. We could change receivers in a matter of minutes, and also improved sensitivity significantly with the addition also of the planetary radar there as well. In 2016, a new ionospheric heater was installed at the bottom of the dish, incredible for studies, HF studies, in particular several DoD interests for that particular capability. And there was significant plans for the Arecibo telescope as well. And so all these scratched out upgrades were projects that were already planned, and the majority of them already had funding assigned to them. And so unfortunately, we've had to cancel all of those after the collapse. But there have been some pretty significant improvement over the last 4 years. And so a lot of those has been increasing the funding from external grants. And so that included external grants from NASA, external funding from the National Science Foundation, and private foundations. We established a novel pay-to-observe program, something that had never been done in the history of the facility. We implemented computer maintenance management systems that didn't exist, electronic inventories that didn't exist, and then also really increased industry collaborations. So collaborations with both private foundations and private industries that can help us drive technology development a little bit further. And so overall, over the last 4 years, we've seen about 30% increase in publication, 10% increase in users, and 20% increase in funding, and 90% in external funding from previously unused sources. So things were going actually pretty well up until the point where we had just a slight problem that we're going to go into here in a minute. But the observatory really is critical research infrastructure, right? It is the only planetary radar with enough power to give us warning time in case an asteroid actually is going to come and hit us. And is the only tool that can characterize the orbit of that asteroid well enough for us to say whether it is going to hit us or not. It is the only atmospheric radar with more than 50 years of continuous data. And that is, if you're talking about space weather, if you're talking about understanding the ionosphere, it's all about long-term data trends. That's how you build your models, right? And so whenever you have gaps in those trends, that's where you start having problems, and that's unfortunately where we're at right now. And it's also been really the most sensitive astronomical tool for studying pulsars and studying gravitational waves right now. And of course, one of 4 atmospheric heaters in the world. So, unfortunately, in August 10, 2020, we started having some unforeseen problems. And so the first of those problems was that we had one auxiliary cable that fell out of its socket, okay? And as the cable fell out of the socket and the attachment point, it damaged the primary reflector. So this picture you see right here is basically the gash that was made on the 305-meter reflector. This is what the bottom of the dish actually looked like. You see all pretty green. It was all, you know, shaded by the reflector panels themselves. And this right here is that cable that was actually broke, the cable that fell, and then it's just slung over a cable that's going to a different tower, okay? And so the cable failure was really unexpected because the cable that failed was actually the newest of all of the cables that had been installed. And so when the observatory was built, it originally did not have this Gregorian dome that you see right here, right? That, as I mentioned to you, was an upgrade that was done in the 90s. As we did that upgrade in the 90s, since it was significantly heavier than the structure that was there before, new cables were installed in order to compensate for that extra load. Those cables are called auxiliary cables, and we added 2 cables from the platform to each tower, so 6 cables in total, and then 2 more cables from the tower to the anchor point, okay? So again, per tower, we basically added 8 cables that would help us maintain the extra load of the Gregorian dome itself. Oh, let me go back here. I want to show this picture because it gives you at least a little bit of an idea of how complicated that structure really truly is, right? So it's, you're talking about 900 tons up in the air that are suspended, taking on pretty heavy winds, taking on earthquakes day after day. And this is sort of how it looked like. But this is a more detailed configuration. Again, these were your main cables. So this that you have here are the original cables that were installed when the facility was built. And this is one of the auxiliary cables, and that's one of the other auxiliary cables, okay? Now, these are the cables that go to the platform on this side. On the back side, these cables go to the anchor point, okay? So there's 3 anchors, 1 for each one of the towers. And we had 5 backstay cables that were originally installed, and then the 2 auxiliary ones that were installed in the 90s. This is what your anchors look like, okay? And this is just another view of that same tower, which just gives you an idea of where these cables are located. When the first cable fell, the the way that it failed, again, was so unexpected because you would have expected, I think, maybe a fatigue failure of sorts or your cable snapping because it had lost capability throughout the years, or your strands had broken throughout the years and you know, slowly lost capability to the point where it snapped. That's not really what happened. What happened is that this is a picture of the inside of the socket, okay? And so the outside cables, as you see them, all snapped, and the center of the rest of the cable just slipped out, okay? And that's the chunk that you're seeing right here, okay? A very, very highly unusual failure mode for this type of socketing and cabling structure. By the way, this is how all of our bridges are built. The majority of our suspension cable bridges are built exactly with this same cable, sync socketing, and spelter socket technology. And so right after this happened, we put together a repair team very, very quickly with structural engineers, forensics analysis firms, cabling experts, and started putting a plan for how are we going to go repair this thing. So first we had to build a model that would help us at least show some capacity because we had to put people up right in the towers to be able to do this repair. And so we had to make sure that the staff was going to be safe while they were doing this. So we needed to understand to a level what capacity we had left. So we spent quite a bit of time modeling. There was a lot of concern over, you know, how good are your cables, right? How good are your auxiliary cables? Are we going to see another one of those cables slip while we're doing this repair? And you have a crew up in a tower that's 500 feet in the air, right? And so these were kind of the considerations that we were going through. And so the decision that was made was, hey, let's go and anchor all those auxiliary cables. Let's put clamps on them. Okay, we'll put a friction clamp on it. So in case they slip out of the socket, we can still hold on to them, and then it's not really going to collapse. And so we began fabricating those friction clamps that were, you know, fairly complicated. As you can see here, you have just a couple of rods and then some steel parts that are going to do most of the friction. And then we said, okay, well, we'll install those clamps. We'll make sure that we can secure those auxiliary cables that are not going to fall off. We had installed some monitoring already, so we had an idea of the loading, at least on the auxiliary cables, and how they were going. And from there, we're going to go install a new cable, a new auxiliary cable on the north end of Tower 8. And then we're going to go changing all those auxiliary cables because we don't trust them anymore. Okay? So that was really the original plan. So we began ordering clamps and ordering cables to just accomplish just that. Unfortunately, on November 6, 2020, a main cable failed. This time, it did fail in tension. It did not slip out of the socket. It failed in tension as if it had been overloaded. At no point during the analysis process was there thought to have been degradation in the main cables, right? The suspect cables were the auxiliary cables the entire time. So at the point that your main cable fails, now we know we have a really, really big problem because we don't really understand the capacity of the structure. Okay. And then if you can let me play the video there real quick. On December 1st, 2020, then we had a second main cable failure, which led to the collapse of the entire structure. And so this video here was taken with one of the drones that we used at the facility to inspect the cables. And you can see the collapse. So that's about 900 tons of steel there, dropping about 600 feet. And so we were coincidentally flying the drone. We inspected those cables about 3 or 4 times a day. The crew that was flying the drone had just finished their initial inspection in the morning, but then heard one of the wires snap in another cable. And they said, you know what, let's just take another flight out there, see if we can identify and pinpoint which wire broke. As they were filming that, then they caught the collapse. As you can see, the collapse not only, you know, took of course the telescope itself and the platform, severely damaged the primary reflector down in the bottom, and then also all 3 tower tops were cut as well. Okay, right? So they just cracked. And so from a damage perspective, I think that the major scientific instruments we had talked about earlier were lost with the 305-meter telescope. So that includes the planetary radar, it includes your incoherent scatter radar, and it includes all of your astronomy receivers as well. Okay. The primary reflector lost about 35% of its panels, and it's, of course, completely misaligned. And then we also have infrastructure damage on several buildings. So about 5 different buildings received some sort of damage, either partial or complete, from the cables as they fell down and actually impacted some of the structure, especially very close to the visitor center where Tower 12 is right next to that visitor center area. And then the ionospheric heating facility, we had 6 dipoles, 3 for each one of the frequencies, and we lost 4 of those 6 dipoles as well. Now, the things that were not impacted were your LiDARs, right? Your LiDAR laboratory, your optical laboratory, those are okay. We have a remote observing facility out in the Culebra Island, which is 10 miles to the east of the big island of Puerto Rico. And so that wasn't impacted either. All sky cameras are fine. Your incoherent scatter radar transmitter, your actual transmitter equipment was not located on the platform, is located in building 1. And so that is still intact. And then your ionosonde and your HF transmitter also located separately from your HF antennas. And so at least your transmitter equipment is okay in case you're able to replace those antennas and restart observations. The current status of the facility is, so we've been basically doing environmental remediation, removing debris for the past year. We've completed the removal of the debris from the site, and so this is kind of now how you look at from the bottom of the dish. This area right here is exactly where the platform fell, and so we're of course able to remove all of that, and now we have coconut matting there, helping plants regrow in that area. We have removed all of the damaged panels, and we have also made the decision in conjunction with the National Science Foundation to leave the remaining power panels that are still good as is, in case there are ideas for rebuilding that into the future. Okay, so that decision has not been made, but the panels are still there. So only 35% of the panels have been lost. And then we've also sealed the top of the towers. So all 3 towers have been sealed, the tops of them, and actually you had to cut them off so there was no debris left up there. And then we are actually just finishing the sealing of a crack on Tower 12 that should be done by next week. And with that, we should be complete with the immediate environmental remediation and the immediate site restoration. Okay. We also established a salvage committee that included both internal stakeholders and external experts to help us identify pieces of the telescope that we could say that were of significant cultural or historical value that could be perhaps used in the future for education purposes or to sit at a museum. And those items have been identified and moved to a different location. So we did salvage as much as we could from the debris before we removed it from the site. Of course, from a science perspective, the instruments that were not impacted have continued operational, right, throughout this entire year. So the observatory itself is still operating. We just lost, our most powerful instrument. We are also spending quite a bit of time doing some forensics analysis, trying to understand why did it fail, and what could have been done to prevent that. And so we had 2 different teams working on 2 different analyses. The first one is with Jenny Elsner, who was tasked originally with performing the forensics analysis for the failure of the first auxiliary cable. Okay, so they had that one socket, and they were doing testing in conjunction with the NASA and Kennedy Space Center to determine, what happened with that one socket. And so right now, their report, which was submitted to changing? This better? Okay. So we're taking over doing some much more detailed analysis and engineering to try to understand the entire collapse. That includes, as you can see here, some pretty complex wind loading, wind modeling, and then we also are doing full-size scale testing of old sockets with new sockets, existing cables, et cetera, to try to understand whether the initial assessment from WJE was correct or whether there is new data that we need to add. But that final report was actually submitted to the National Science Foundation, is not yet public, but probably will be here in a couple of months. Okay. Let me see if I can move this forward. No. Doesn't like me anymore now. Okay, there we go. So, what's the impact to the capability of the U.S.? Well, it's pretty significant in our mind, in particular with the loss of the planetary radar. Really, there are only two facilities that can help characterize asteroids to the level of detail that we would need in order to send a mission to one of them. The DART mission, for example, that was done. That particular asteroid was selected because we had all the telemetry data from Arecibo. And we don't have that anymore. And the Goldstone facility, which is the remaining planetary radar right now in the U.S., it has 45% of Arecibo's power and only 10% availability. So very little warning time if we really needed to understand and map the surface of an asteroid or a near-Earth object, right? Similarly, long-term data trends are now getting significantly impacted with the loss of the atmospheric radar, which we had continuously operated for over 50 years. And also have significant impact to our ability to perform radio astronomy, right? We basically lost about 70% of the available open skies time on single dish astronomy because we don't really have that many large facilities, right? We had the Green Bank Telescope in West Virginia and Arecibo as kind of our two larger telescopes. And with the loss of Arecibo, now we're at a point where are we going to get our science done, right? And so that leaves us with using other telescopes to do this type of science, and it's not as easy because telescopes, particularly newer telescopes like ALMA and other radio telescopes, are built to operate at really, really high frequencies. And so we operate on the low end of the spectrum from 327 to 10 or 12 gigahertz. So there is a big gap on that capability. Now some may say that China has, right? The China FAST telescope, which is a 500-meter telescope, they operate in similar frequencies. Yeah, but they're in China. And so it's not as easy to get access to that telescope, much less without having to build collaborations with their Chinese nationals as you're taking those observations as well. So we're at a point where we have China and we have Europe investing heavily both in radio telescopes and in radars. And so right now, iSCAT 3D will become the most powerful atmospheric radar in the world. And the SKA telescope in South Africa will also dwarf the US VLBI capability here pretty soon. And so we need to start thinking about where are we going to be investing for our next generation telescopes. So where do we go from here? Well, we have some ideas of where we think we need to be going. Can you help me move to the next slide? For some reason, the clicker is not working. Okay, perfect. So first thing we're doing is we're aligning all of our short-term science to our existing capabilities, right? So in astronomy, we're using our on-site 12-meter antenna for observations. That is going to be part of both the VLBI network and the European the EVN network by January. Okay, so the teams have been working on retrofitting that antenna for VLBI observations. And then also we're really going to be working with historic data sets. And so one of the key accomplishments I mentioned earlier was we were able to move all of Arecibo historical data sets to the Texas Advanced Computing Center. So now we can use cloud computing to really process a lot of those data sets faster, and we can also revisit older data sets, right? So we have data sets dating back to the 60s, and back then we didn't know what an FRB was, right? Back then we didn't know what an exoplanet was, and so now we know. So we have a lot of years of data that we can go back and use, and we can do that automatically using artificial intelligence and machine learning algorithms. On the atmospheric side of the house, our focus has shifted to LiDAR and optics, which is all the available equipment we have both on-site at Arecibo and at the Arecibo Remote Observing Facility in Culebra. And on the planetary side of the house, we've rescoped the grant to really focus more on data archiving and analysis and shape modeling, right? And so shape modeling is a big deal for near-Earth objects. Typically, it takes a researcher anywhere from 6 to 8 months to create a shape model for an asteroid. So we're really going to be trying to use more computing power and some machine learning algorithms to try to at least reduce that to half the time. And so that way we'll be at 3 to 4 months instead of 6 to 8 months to do a single shape model. So that's on the really, really short term. What else have we done? Well, we've started thinking about what are the options that we want to do for what we're calling transition science or midterm capability. And so we've submitted right now 5 different proposals that have different midterm capabilities that could be implemented immediately at the Arecibo Observatory. The first one was a proposal for a new antenna that would be the VLBA site number 11. So we have proposed the installation of one NGVLA antenna. And so for those that are not familiar, the NGVLA stands for Next Generation Very Large Array. This particular project, the proposal for that project is really 244 antennas that were going to be distributed in the U.S. And other territories, including Puerto Rico. Puerto Rico originally the Arecibo site was slated for 3 of those NGVLA antennas. And so we are proposing to install one immediately so we can help with commissioning the NGVLA project overall and then also create a new VLA site, right? So it seems to be a win-win situation. We've also proposed another idea that has been submitted to the Mid-Scale Research Infrastructure 2 call from the National Science Foundation, and that is called the A06 Project. So that is the installation of 6 of those NGVLA antennas on the Arecibo site, but we would retrofit them with a planetary KU radar, KU band radar. And the idea for that is really for us to begin testing what phasing looks like in this type of antennas, because we're going to need it for the long-term solution, right? So we're kind of baby stepping our way there. And then we've also proposed the installation of a next-generation incoherent scatter radar. So the AO-MISR would be similar to the current modular incoherent scatter radars installed in Canada and Alaska, but they would be about twice in power. So we would basically have the most powerful incoherent scatter radar again back at Arecibo. This is existing technology, so it's not like you're really jumping a whole lot of hurdles to get there, and could be done in a very, very short time frame and would enable some really great science in the medium term. In addition to those proposals, we've also submitted a proposal, and this one has actually been awarded for a new radio science center that's going to be helping develop some of the RFI mitigation technologies that we could potentially use for other radio astronomy observatories. And we also had a DoD proposal for a new digisonde, not located at the Arecibo Observatory site, but at the Solar Observatory in Aguadilla, so it's about a 20-minute drive. And that is also under review. So we've been pretty busy coming up with what can we do in the short term, what can we do in the medium term, making sure that the National Science Foundation and the funding agencies have enough options to be able to make decisions here in the medium term. But even with those medium-term capabilities, there really is still a need for an anchor instrument, right? This type of facility, all those midterm capabilities don't replace the capabilities that 305 meter had. It gives you additional capabilities that helps you understand a different technology a little bit better. It's going to be a different suite of electronics. It's going to be, you're going to understand how to do phasing with some of these radar beams, and that's great. But it doesn't replace the capability. And that's the challenge. So in our mind, we really need to be thinking a little bit bigger than that and thinking not only how can we get back the capability we lost with the 305 meter, but how can we make it so much better than anything that is out there right now, anything that is in an existing facility or in a planned facility in the next 3 or 4 decades, right? And that's the challenge that we put forward to our team at Arecibo. and said, if you had no constraints, what would you build? What would you want to have, right? What do you need to really do cutting-edge, great science? And so we came up with this concept, okay? And we're calling it the Next Generation Arecibo Telescope. It's called the NGAT, so you're going to hear that a lot in the next couple of slides. And the concept of this particular telescope is very different from existing telescopes. It's not a single dish, as you had seen as the old Arecibo Observatory, the legacy telescope was. And it's not a phased array, right? It's not a lot of little dishes that are spread around a large area. This is a compact phased array. So it's trying to do the best of both worlds. It's trying to give you the sensitivity of a single dish with the flexibility to be able to point to more areas of the sky that a phased array gets you. Okay? And this is the concept. And so the NGAT really is a community-led initiative, really started by the Arecibo science staff and also the Arecibo users, and then slowly more and more people wanted to collaborate and provide ideas on what should be that replacement instrument at Arecibo. And a white paper that, in my opinion, is a very, very high-quality white paper was submitted describing that concept and describing all the science applications that would align to that. And so from that, we came up with what do we need to do that great science. And so this is what we need. For planetary, we would like to have 5 megawatts of continuous power from 2 to 6 gigahertz, right? So similar to where we were, right at S-band, being able to go a little bit higher than that. But multiplying by 5 the power that we had before, okay? Similarly for atmospheric sciences, the idea is to be able to observe at 0 degrees and 45 degrees. So you could actually take parallel and perpendicular measurements of the geomagnetic field, but you would like to do that at 10 megawatts instead of 2 megawatts. Okay. There currently does not exist a radar that has 10 megawatts of power. We just don't have it. Okay. So this would be a first for humanity to be able to have this type of power in incoherent scatter radar or in a planetary radar. And in radio astronomy, our idea is to go from 200 megahertz, which is a little bit lower than what we had before, all the way up to 30 gigahertz, with a sensitivity that would actually dwarf fast sensitivity right now. And at that frequency range, it would be better than both the SKA and it'd be better than the NGVLA for about a third of the cost. So, next slide, please. So these are the key science goals, okay? So we're basically taking a lot of the basic research and science that was done at Arecibo with the legacy telescope and just amping it up to the things that we've really wanted to do for a long time, but we haven't had the capability to do, right? And so from a planetary side of the house, we're talking about really increasing the amount of near-Earth objects that we can characterize, going as far away as we think we can get there. So that would mean we can study the ocean worlds around Jupiter. We can observe asteroids in the outer region of the main belt. And so these two things have never been done. Okay, we've never had technology to get there, radar technology to get there. From the atmospheric sciences perspective, we really want to continue to understand climate change. How does global climate change happen? How do we better understand the ionosphere to a level that we've never been able to map before because we haven't had enough power to really get the data? And so getting to 10 megawatts would really provide really finite data points for us to better understand how the ionosphere works. And in radio astronomy, it's just the cases are just amazing, from understanding gravitational waves to dark energy and dark matter, supermassive black holes, pulsar science, of course, has always been a critical science at Arecibo that will continue to be there. Star formation. I mean, it just opens up a whole new fields for science to be done with this new Arecibo telescope. And so we started then defining what the concept would look like, right? We had the science goal. We knew what we wanted to look at, what we wanted to find out. We knew what we needed to get to that science, right? So we knew the power levels, we knew the sensitivity levels. Now we really needed to understand what would this thing look like. And so we started exploring with different ideas. And we explored with a single dish, you know, could we put another Gregorian up there? Could we do a Cassegrain design? That would be proven. But then we would run into the same constraints we had before. Well, we don't have enough field of view, we can't look at the galactic center, you know, cost is, you know, still significant to rebuild. Your sensitivity wouldn't be a lot better, so you'd be paying a lot of money to get the same thing that you had, you know, 30 years ago. And so that didn't kind of make sense. We talked about an array, but then the array would have to be so large that you'd need it at least 3 times the amount of land that you would have at Arecibo. And then at that point, you have the NGVLA. And so it just didn't make sense to replace it with an array. And then we thought about, well, what if we do a hybrid? And that's kind of what you see right there on that top right-hand side. What if it's a single dish that has smaller dishes in the middle, and those kind of pop off and can point in different directions? And that seemed like an interesting idea, although it didn't really get us the sensitivity that we would have wanted to. And so we kind of ended up scrapping that, but that led us to this array of dishes idea, where we said, well, what if we put all of these dishes on a flat plate? Okay, that solves our problem of being able to move it, because you don't have to move all individual dishes, we just move the entire plate. But then you still have the flexibility of having all those beams if you have your radars, right? So let's say you can put a radar beam in each one of those 1,000 different 9-meter dishes, for example. Now you're getting a next generation instrument that's never been done before. It's never been built. And so the next slide just gives you, and these are artist concepts, but kind of gives you an idea of how the team kept iterating, right, and changing what was in the art of the possible, right? So originally, the thought was, well, we'll have this giant plate, right? We'll put all the reflectors on top of it, and that's what you see here in these pictures. The ones on the left-hand side of the screen are actually kind of embedded into the structure. Ones on the right-hand side are on top of the structure. They'll kind of do the same thing. But we ended up with a concept that said that we needed a little over 1,000 of these 9-meter dishes to really get to where we wanted to be, and that's in our next slide. And so it's basically 1,112 9-meter reflectors, gets you the highest sensitivity on the planet, gets you the most powerful planetary radar in the world, the most powerful atmospheric radar in the world, 250 increase in sky coverage from what you had before, and RFI cancellation technology. So whenever you see that dome, by the way, that's what it means. It's not that is a physical dome that is on top of it. It's just that the cancellation technology that will help protect the radio astronomy frequencies. I like to mention that because some people look at it and say, oh, what's that dome? No, it's not really going to be there, okay? It's like, well, yeah, that'd be a complicated dome to build. And so those are, and you know, we can do this maintaining our key science goals. Now, as we started thinking a little bit more about this, right, and we start going from concept to what would it take to make this a reality, the biggest, the biggest unknown, or the biggest concern from the science teams was not the science, was the structure. And so they were like, well, can you really build a plate that's that big that's going to go move 45 degrees up in the air? Right? And how much is that going to cost you? And how much is that going to deflect as you start moving that up? And how do you control that deflection, right, to maintain the sensitivity that you need? And those were very good questions. And so we kept thinking about it and had some of our structural engineers kind of come up with some numbers. Is that feasible? You know, should we do that? Should we try something different or do something else? And so they came up with this other concept that kind of provides the same logical idea, but in a way that we can actually build it. And so we've basically decided to split this in 7 panels. And yeah, maybe let's play the video there real quick. Perfect. and we can have them tilt, and we can have them rotate. And they'll rotate on a single rail. So it's not very complicated for them to move. But when they're pointing up, this is when they're flipping it back, you have very, very minimal shadowing as you do this. Because you have them, see, right there at different elevations. This also allows you to do this project in phases. And so you don't need all 7 to be done at the same time. You need 1 to get started, 1 phase. And then you can build your second. By the time you build your 3rd phase, we've calculated you already have more capability than what you had with the old 305-meter telescope. Okay. Next slide, please. And so the expected performance. On the astronomy side of the house, basically the NGAT's expected performance would be more sensitivity than FAST and more sensitivity than NGVLA up until about the 12 gigahertz. But the survey speeds would be faster than anything in existence as well, just because you're moving all of those dishes at the same time. So your survey speeds is just incredible. Again, you know, outpacing both NGVLA, SKA, and of course the GBT and FAST telescopes that are already in existence. Next slide. And so for these, and you know, this we had used for previous presentation, this just tells you an idea of whether NGAT would be appropriate or not, or which telescope would be more appropriate for different types of existing projects that are of high priority to the science community, right? And so if you're looking at searches for FRBs, NGAT would be able to do the job, right? Better than FAST, better than the DSA. For the studies of low-frequency gravitational waves, it'd be better than FAST and the DSA. For extragalactic H1, it'd be better than the DSA and FAST, right? And it has synergies with NGVLA. So they can coexist because they work in different, they're focused on different frequency ranges, right? So the higher frequencies, NGVLA is going to be fantastic for that. I think it's going to be a great instrument. But on the lower frequency range and on the radar capability, then the NGAT concept would basically dominate. Next slide. On the SAS side of the house and on the planetary radar, you're going to see very similar charts to this. There's just nothing that compares. I mean, there was nothing that compared to Arecibo to begin with on the Incoherent scatter radar when it was 2 megawatts. Now when it's 10 megawatts, there's just nothing out there like it. So we didn't even spend a whole lot of time comparing it to anything else. So on the planetary side, on the next slide, you're going to see something very similar, right? You know, the capabilities for NGAT alone, and as you look at that chart on the top right-hand side, that compares the detectability of asteroids with a diameter of about, let's say, 140 meters, which is what we call the ones that we focus on tracking. NGAT gives you the best detectability of anything else. The only thing that compares to that detectability would be a GBT radar to NGVLA receivers. And so it doesn't get you as far out, but it gets you pretty good results. Now, if you would do an NGAT radar to an NGVLA receiver, then at that point we can't even map it, I think, on that chart. So, okay, next slide. Now, that being said, there are a lot of challenges. There's technical hurdles, a lot of them that need to be understood and addressed, and then there are programmatic challenges, right, that we need to manage. The technical ones, and I just named a couple because those are the ones that we're kind of trying to work our way through slowly, are grating lobes, the transmitter phasing that has never really been done at this scale and at this power level. The best that I think we've done with transmitter phasing has been 5 antennas done by JPL. So we need to move that from 5 antennas to 1100. So that's not a simple task. And then the cryogenics are a big problem, right? If you have 1100 antennas that are cryo-cooled, That's a lot of weight. That's a lot of cooling for a lot of those receivers. And so those are two of the bigger things that drive cost, that drive weight, that drives cost again, that drives maintenance costs in the long term that we are still working on how to manage, okay, and how to mitigate. And that goes to the recurrence maintenance cost. Now, on the programmatic side of the house, there are other challenges that are not technical, right? The timing of this collapse is horrible. And it's horrible because it happened right after the Astra 2020 decadal survey. And so the community, the Arecibo community, had submitted over 25 white papers supporting the use of Arecibo for a variety of high-priority science projects, but we were not allowed to submit new ideas because the deadline has passed right after the telescope collapsed. And so it's unfortunate that some of these ideas were not able to be captured as part of the Astra 2020 and now have to wait 10 additional years before they get into a new decadal survey. So that is the timing is quite unfortunate, I think, from our perspective. There's also other timing issues, right? NGVLA investment is now highly recommended, so there's not that much money to do a lot of these big projects at the same time, and the NGVLA is a high priority project that should be executed, and it is highly recommended. So, you know, it's unfortunate that they're both competing now at the same time for similar amounts of money when they really shouldn't. And in addition, there is also a little bit more uncertainty on the management side of the house, just because the current cooperative agreement for the management of the facility ends in 2023. And so basically that's only one more year, a year and 3 months, before a decision has to be made on who continues to manage this facility for the National Science Foundation, whether they're going to be recompeting that contract or whether they're just going to continue to extend the current management team. So that adds another level of uncertainty to the long-term planning for the facility. And in addition to that, I think the other two big issues are community consensus. While there is a lot of support for the concept, getting that consensus in an official manner, as we would, let's say, in a decadal survey, it takes time. It takes a lot of time. And so if we are going to be expecting that type of consensus building for this project, then you're looking at 10 years at least before you can get even enough support from the broader community to be able to push something like this. And then finally, the sticker price, it's not like it's super cheap, right? So we're currently estimating the cost of this to be right around $500 million, which really isn't an incredible amount of money when you compare it to other telescopes. Okay, as I mentioned, NGVLA's expected cost is $1.5 billion. And so $500 million is not extremely expensive for this type of capability. Okay. Next slide. And so this slide just kind of summarizes what we think are the timelines and the capabilities that we're going to have available at the Arecibo Observatory, or that we could have available at the Arecibo Observatory if every one of the projects that we've talked about actually comes to fruition. Yes, this is highly unlikely, okay? But it's a nice way of presenting how they blend together one with the other. And so we would expect immediate capabilities from the 12-meter antenna, from the Advanced Data Analytics, and from the Radio Science Center. The HF facility, the actual dipoles have been fixed. And so with the dipoles fixed and your transmitter not damaged, could be operational if you put a little bit of work into the primary reflector, okay? So that is a possibility. That is not very complex. And then you would have your three mid-scale projects, right? Your VLBA11, your A08, and your AOMizer. And the A08, actually, that became A06 now because of funding constraints on the mid-scale research infrastructure 2 call. So that's why it says A08 here, but A06 on the previous slide. And that on your AOMizer would allow you to do great medium-term science for the next 5 or 6 years while you're doing detailed design, detailed planning for the NGAT project to finish out in 2030, okay? So we do understand that something like the next generation Arecibo telescope is not something you design in a year or in 6 months, right? It is going to take us 9, 10 years before that the technology development that's needed happens, and before we actually complete the build of that telescope. But that's why those mid-scale projects are really important, because it gets us medium-term capability, and those mid-scale capabilities helps us actually lower our risks on the NGAT project overall. So they do build on each other. And so just to close out, you know, the observatory has really been a critical facility for over 55 years. And I think there's not been very many other telescopes as productive for such a long time as this one. And I think it's provided invaluable contributions to human knowledge. It's had invaluable contributions to STEM education, to informal education in Puerto Rico and across the globe. And there's nothing to replace it right now. There just is not. There isn't another instrument that is either in operations or being planned that can actually replace its capabilities. So it is an instrument that is something that we just need to think about, right? We had this capability, we lost it. Are we just going to let it go, or are we going to think about building something better? Are we going to think about bringing something that's a next generation capability? Now, in terms of the site remediation should be done by the end of this year. So we're really excited to get out of cleanup mode and picking up debris and do environmental assessments and so on and so forth, and get thinking more into how do we start now building something new. Now, it's short-term science goals. We have aligned those with our existing capabilities, and we have, as you know, a range of proposals and capabilities that can give us great midterm capabilities for the site. And of course, we do believe that an anchor instrument is needed at this facility, and that the only way that we're going to be able to fill that void left from the collapse is by building a new radio telescope that has much more technology and much more capability than what we had before. Well, that's, I think, what I have for you all today, so thank you very much.
Well, thank you very much, Francisco. Let's hope we start this shovel-ready project right away.
Almost.
Now we have time for the Q&A. There was a procedure for questions for those of you who are here. If you want to ask a question, raise your hand. Be persistent. Eventually, one of the runners will bring you one of the color-coded microphones. It will be on, and you don't need to do anything to turn it on or adjust the volume. Just hold it the right distance from your mouth, which is about this far. Okay? I will call on questioners by the color of their microphones, because I know most of you, but not all of you. And when I call the color of your microphone, please stand up, tell us if you're a member or not, and ask a question. Please no speeches, that's for afterwards, just questions. And when you have asked your question, hand the microphone back to the runner so that they can bring it to another questioner. Please keep in mind that we want your questions to be clearly audible to YouTube viewers and to those who watch the recording later, which is the majority of the viewers who will watch this lecture. So it's important to hold the microphone close, but not too close to your mouth. YouTube viewers can text questions in the YouTube chat box, and these questions will be read aloud to the speaker for everyone to hear. So, do I have any questions? Frederica, we need a microphone up here in the front. Please stand up so they know where to. Frederica has the red microphone. Are we good? Red microphone? Okay, we're going to exchange for the blue microphone. Sorry. Don't do anything, Frederica, just talk. Let's hope it's on.
Perfect.
So I can go ahead with my question. Hi, my name is Frederica Derima, and thank you very much for a kind of a comprehensive presentation of the history, the subduing situation of the collapse, and also the future plans. And I have many questions, but I probably would like to, for the past, but I would like to go for the future kind of proposals. So you talked about, you know, a timeline. First of all, the decadal surveys are great, but I'm not sure in this situation that there is anything sacred with a decadal survey, and an emergency kind of meeting by the scientific community cannot be kind of put together to, in a sense, bring a consensus within a year or so. Because you did talk about the cost, you know, and yes, when, I was thinking, wow, this is $1 billion and more kind of for a couple of billion maybe. So when you said 500, yes, it's a modest amount. However, what is the timeline? Because the timeline is at least 10 years, you know, even at the best kind of conditions, right? And also the design, the modular design that you kind of showed, that is also an interesting idea. And you said it can be done in phases. And so what would be the timeline for that be? And let's say if you have 1 of the 7 or 3 of the 7, what science you can demonstrate to, in a sense, create the impetus for the rest of the completion of the whole 7 modules. So,
you want to repeat the question? I'll repeat the question just to be sure everybody could hear. I believe the question was, at the end there, what is the timeline for completion of the whole project? And in particular, what's the timeline for completion of 1 module or 3 modules? And 3 modules in particular, because you said that would give us greater abilities than the old Arecibo Observatory had.
Yes, so no, very good questions on timelines, and so it's very hard for us to determine the length or the timelines for executing a lot of these projects without really knowing the financial constraints that are going to come associated with it. And so if it was in a perfect world and we had $500 million on the table right now, we think we can complete that project from 5 to 6 years. Okay, and that will be for the whole thing. Okay, that is, of course, again, money's there, start spending, go, start designing, and go. As you know, that's not how it happens, right? And so we're going to go through proposal writing and reviews and evaluations, and and more reviews and more evaluations. And we're going to do preliminary design, and that's going to get evaluated, and then we're going to come back and have a review panel, evaluate it, and then we're going to submit, for the next design. And so that's really where that that effort kind of expands out into the 10-year process, just because we're adding kind of 4 years of, we're going to have to spend some time either writing proposals or evaluating. But we feel that from 5 to 6 years should be an acceptable amount of time to build it. To do 3 modules, I would say maybe 4 years. We haven't really done the math yet of exactly how much it would be. Now, we have to consider that based on the conversations we've had with suppliers, based on the conversations we've had with the community members, to be able to calculate cost of fabrication, there is a large amount of savings from doing mass fabrication of things, right? So while one may think that it's a lot less costly to build half of it, it may not be, because your component costs are more expensive because you're buying less amount of them. And so there is, there is a 10 to 15% savings for you going on a larger scale. So that would have to be considered at some point. But I would say that probably 4 years, 3.5 to 4 years for the three phases that we talked about. That would give us, for the most part, comparable sensitivity and comparable power to the legacy Arecibo telescope.
I have a couple of questions for you. Looking at the concept drawings, it looked to me like, would be fair to say, the engineering, structural engineering, is not all that challenging. It's a kind of well-known construction techniques and
Yes.
loads, but what is involved in the dishes? Are they going to be like the Webb telescope reflectors, which ended up being very, very difficult to fabricate, or are these more well-known techniques?
So I'll say this. Whenever an engineer asks the questions, they usually think it's the science is the complicated. When a scientist asks the question, they usually think the engineering is the complicated part. That's just that, and that's been, trust us, for the past year, that's where we've been going back and forth. But I'm an engineer, so I agree with you. The structure part is a lot more simple, I think, in general. And I think this, you know, the concept where you saw the 7 phases, that's got some analysis behind it. So it is doable, right? It's not unfathomable to build it. It's not, you know, an unimaginable cost or anything like that. It is a doable thing. The reflectors in radio astronomy, these reflectors, while they're going to be of a lot higher quality, the surface, than what we had on the legacy telescope, because we do want to get to the 30 gigahertz, so we have to be a lot more accurate. They're done already on a lot of other telescopes. So you're not reinventing the wheel on these 9-meter dishes. They exist. You can actually go and order 9-meter dishes right now that would have this level of sensitivity. Now, where the challenge comes is on the radar technology. That's where you have more hurdles that you have to jump. Doing the phasing, it's a little bit more complicated. We haven't really done that at that large scale. Managing 10 megawatts of power hasn't been done, right? So there's, you know, oh, people think it's simple. Well, if you've done 2, if you've done 4, do 10. Well, it's not the same thing, right? So I think that's where more of the challenges are going to come. I think when you look at the structure overall, when you look at the reflectors, even when you look at the receivers, these are quote unquote off the shelf, not off the shelf, but this is technology that we know, it's technology that we've proven. And so the technology, the risk of that technology is low. The higher risk would be the radar capability, the phased array radar capability, which can be proved with the A06 project. And so that would be a nice short-term project to begin testing that capability.
Let's go with the blue microphone, Bob Hershey. State your name.
I'm a member. I have a question about how you're going to use the data, of how you coordinate it with the other telescopes and even with the space telescopes like the Hubble and the James Webb Space Telescope.
And LIGO.
Okay, so typically this, for the NGAT concept itself, it would be a standalone radar or data taking system. So we wouldn't be relying on other telescopes to do our science. That's not to do all the science goals that we've listed out here. One, that is not to say that they cannot be part of, you know, interferometry observations with other telescopes. They could be very well and add a lot of value by adding a lot of sensitivity, okay? So we would expect to be part, as we mentioned earlier, to partner with future projects like the NGVLA. That would be a fantastic pairing with the NGVLA. With the VLBI community and with the EVN networks, those type of interferometry observations would still continue. Partnering with optical telescopes is something that we also do as well, but we do it to perhaps either validate some of our data points, or we also use them as complementary data sets. For example, most asteroids and near-Earth objects are actually not discovered by radars. They're discovered by optical telescopes. And so they tell us where the near-Earth objects are, and then we use our radar to be able to map it and properly categorize it. So that's how we would really see a lot of value in things like James Webb, right, and in other optical telescopes that are new, that are going to be fantastic discovery tools, right? They're going to be great discovery tools. But we're still going to need to have, at least for those near-Earth objects, more characterization capability, and that's what we can bring with some of the radar cap.
We have a couple of questions from the web, I think.
No? Oh,
Yep.
there we
Yep.
are. Okay. There's one comment online from Marvin Stadolski. Is there any room for international participation, perhaps with complementary sites built in other nations for more complete sky coverage?
So I think that is certainly a possibility. I think that is also one of the programmatic challenges that that we have is determining who's going to take ownership for this type of instrument. Is it going to be the National Science Foundation? Are we going to do it with an international collaboration? I think all of that is possible. You know, when you go look at ALMA, right, an international collaboration has been done in Chile for those telescopes. I think an international collaboration would be in the art of the possible. Yes.
Another question from our camera operator, Connor, over here. You mentioned the receivers need to be cooled. What is the operating temperature and what sort of cooling technique would be applied?
So it would be they would be cryo-cooled. I don't remember the temperature right now off the top of my mind, but I can get that one to you. The challenge that we really have is the weight that we're adding, where we're adding all those cryogenics to those receivers. It's very significant. And so we had similar situation with the receivers at Arecibo, right? All the Arecibo receivers were cryo-cooled as well. The one thing is we had 8 of them, right? So we only had to cool 8. Here we're going to have 3,000 of them. So it's not, the scaling becomes a problem.
And you said engineering wasn't a problem.
Well, it's solvable.
Did you say there's a 500-meter dish in China?
Yes.
Or it's proposed, it actually exists?
It exists and it's operational, yes. It's called the 500-meter aperture spherical telescope. It's fast.
Could you comment a little bit on that telescope and its capabilities?
Sure. So the FAST telescope was built at some point because we had a lot of interest from China. I'm told this story. I wasn't there at Arecibo back then, but one day they received a group of 20 or 30 Chinese nationals from Puerto Rico with videotapes and cameras and took a bunch of pictures. And a couple years later, FAST was getting built with very, very similar features to Arecibo's. FAST is a great tool. I mean, it's incredibly sensitive right now. They have a different technology where they have kind of a smaller chamber that houses their one receiver, so you only put one receiver at a time. And it's kind of think about a football sky cam. That's kind of how they're moving that receiver over your 500-meter primary reflector. They also have active movement in the reflectors, so their panels move. They have actuators in their panels, which is a good thing and a bad thing. It's a good thing because if you can control them to the point, you get really, really good accuracy. It's a bad thing because they break down. And so you're constantly changing actuators for your telescope to be able to work. But it's a good tool. Right now, it's fixed at the lower end of what our frequency range would be. But it is also only a radio telescope for astronomy applications, so it doesn't have radar capabilities. So they're not going to be able to characterize the orbit of an asteroid. They're not going to be able to do atmospheric studies. They're just going to do radio astronomy, and that's okay. You know, there's very few telescopes in the world that can do 2, 3, 4 things at any given time. So while it is a good instrument, access to that instrument is not completely known, right? And so right now, they have open calls for proposals, and several of the users that were Arecibo users are requesting time and FAST because there's just no other telescope that they could continue to do their science on. But that also comes at a price, right? Again, you have to partner with, you know, one of their scientists and you know, share some of those results with them. So there's a strategic challenge with that type of partnership.
I'm David Rosen, lifetime member at PSW. Are you going to be able to synchronize events you see with the Arecibo telescope with non-electromagnetic telescopes like a neutrino telescope or a gravity wave telescope?
We haven't thought about that, I think, at that point. You know, typically these telescopes do slightly different things, but it's certainly a recommendation, something we can take back and explore.
So with 1,000 of those dishes, it reminds me of the European Extremely Large Telescope and the TMT, where they have a large number of mirrors, and they have in the case of TMT, they have a robotic system to take mirrors out for resurfacing on a regular schedule. Is there a similar idea for these radio telescope dishes to deal with just routine maintenance, or at least to robotically go in there and pluck out ones that malfunction and replace them?
So typically the surface of these radio telescopes is very resilient. Very little maintenance is needed on the surface of the reflector itself. When you get into a little bit more trouble is on electronics reliability, with your receivers and so on. But when you look at the majority of the telescopes, the radio telescopes we have in operations today, they are aligned, at least Arecibo, we aligned it once every 15 years or so. And we did it because we had hurricanes that would impact us, and we did it because our reflector surface was suspended in cables, okay? As opposed to what we would have here now, which is a solid shape. And so really, there would be no need for robotic replacement of those surfaces because the surfaces would not be impacted. There would be need for very easy access to be able to maintain electronics equipments and data lines that would be, have to take into consideration as part of the final design.
And probably the cryogenics.
Don't mention the cryogenics.
Okay, I won't mention the cryogenics.
We're going to solve that one here soon.
We have a question from the web.
We have another question. Am I on? You guys hear me? Thomas Artman asks, what is being done to gain support nationally and internationally for the new telescope? If you can elaborate a little bit more as to what you're doing to...
I think you'll have to take your mask off.
Can you hear me better?
Yeah.
Okay. Thomas Artman asks, what is being done to gain support nationally and internationally for the new telescope?
So when we first completed our white paper submission and rolled out the NGAT concept, we started accepting endorsements from both institutions and scientists around the world. We're up to about 3,000 endorsements right now for folks from that side. But we really need, we're in a little bit of a pickle, and I'll say it because we really need a little bit more funding to be able to mature a little bit of the conceptual ideas into a real design. Without us doing those simulations, without us doing some of that groundwork, we're not ready to go out and say, oh, let's go build it, right? We still need a little bit more engineering and analysis to be done. And that's where we're at. We're at that point where we've done enough to know we have a great idea and a great concept, but we still need to start getting some funding to be able to move this forward. And so hopefully 2022 will bring some of that funding from either private or public sources. But in order for us to even get that, we do need some guidance and some decision from the National Science Foundation to say that they are interested in something like this, right? So, and I think they're still making up their minds on that one.
Given the questions with the radar and the radar power, are you getting interest from DOD?
Yes, typically we do. Folks like NRL and AFRL and Space Force have always had interest in this type of capabilities. When we talk about 5 megawatt, 10 megawatt radars, everybody always gets excited at a lot of high power levels. So there is some interest. Again, this is a National Science facility, National Science Foundation facility, and so it's up to them also to help make a decision on what would they like to see in the future of the facility.
So we have a blue microphone. Just give it a second for the volume to be turned up on the microphone. Please stand and tell us your name and whether you're a member.
Bobby Baum, not a member. I'm wondering, you mentioned that only 35% of the dish was destroyed. Have you looked at the possibility of something like a single instrument on a sky cam to get useful data, like maintaining the continuity of those atmospheric observations? I would think that the weight of something like that would be under a ton compared to 900 tons, the thing you had there before. So it sounds very simple in comparison. Even with the damaged towers, you could probably rig something. You know, ham radio operators might be able to rig something like that.
No, very, very good question. Yes, we've definitely considered that because technically fixing the primary reflector is a very doable thing. Yeah, it takes money, it takes time. There's nothing too complicated. It's just buying panels and putting them down there after you fix the cabling structure underneath. The little bit of the challenge comes in when you try to put the Skycam type of a system that your towers are now too low to be able to focus. And so now you have to build on top of towers that have degraded capability. And one of the ideas that at some point was presented and discussed was putting a metal tower on top of that concrete structure just to give it enough height to be able to hang something something like a Skycam type of a receiver there. And so that would be easy for astronomy. And that would be an easy way of getting, let's say, some drift scans back up and running, getting some astronomy going. It would be a lot more complicated and costly for the radar technology. Because at that point, you would have to have your power generation, your klystrons, or if you're not going to be using klystrons, whatever other amount of power, system you're going to use for power generation, in the dome. The moment you do that in your Skycam, now your Skycam is really heavy, right? And so, and that's why the Chinese haven't done it, right? The Chinese also had to make that decision and said, now let's just stick to astronomy, because the moment that we start adding radar tech in the sky, then it's a little bit of a problem. But yes, it has been considered. It's actually one of the options that was provided to the National Science Foundation on some of the discussions that we had for short-term capability.
Please use the microphone.
You could do bistatic observations. Yes, if somebody else has a radar. Yeah, he asked, could we do bistatic observations? If you fix the primary reflector and you had this Skycam type of a receiver there, you could do bistatic observations if you had somebody else sending the signal.
You might mention what bistatic operation is.
So that means basically somebody, you would have another telescope that would be sending the radar signal, and we would be receiving that signal at Arecibo. So we would do that pretty often when we were doing characterization of near-Earth objects. We would either do bistatic observations with Green Bank, for example, where we would issue the signal and Green Bank would receive. We were actually planning on doing at some point with FAST, where we would send one and FAST would receive. That would have been interesting. We never got around to that one.
I think I'll close with one question to ask you, a kind of retrospective question. How much data is there from 50 years of observation, and what are you getting out of it now that you can analyze it with the sort of computing facilities you have and the AI algorithms that you can apply?
Yeah. So I don't know the number exactly. It's just been terabytes and terabytes and actually petabytes of data, and we're still transferring. And so we should be done with transferring the data sometime in either late December or early January. Once we have that there loaded, then we have to reorganize it, and then we can start doing some of the research aspects. So we haven't even started looking at some of those historical data sets. We've just been finding a way to get it into the cloud. And part of it is, remember, a lot of these data sets are in tapes, right? And so the tapes reader don't exist anymore. We have one tape reader.
What are those?
Yeah, well, and so it's taking a long time to get that data out of the tapes and into a format that we can manage easier with today's computing.
Is that data, is it raw data or has it been partially processed? What kind of data?
So we have
is
both. We have both the raw data sets and then partially processed data. Typically, it depends on the community. Different communities like it in different ways. We do provide partially processed data sets for the atmospheric sciences community, and we do load that into the Madrigal data sets. But there are other observing modes that's just like the raw data. The planetary radar is also data that is processed. The astronomy, we have both. We have some people that want the raw data. We have others that want it processed. So it depends.
Very interesting. I look forward to seeing this project actually get underway. I thank you very, very much for coming and speaking with us.
Thank you, Larry.
Before you go, we have one small token of thanks for coming and spending time with us. It's a signed copy of the Bulletin of the Philosophical Society of Washington, the first volume, which lays out why the society was founded, who were the founders, why it was called the Philosophical Society of Washington, instead of something that we would all know and recognize today, which is the Science Foundation of Washington. And has some of the original presentations in abbreviated form, including a discussion of the ether that you may find interesting. And with that, thank you so much.
Thank you.
Before you go, we have a few announcements to make. The 2,451st meeting will close the fall lecture series on Friday, December 17th. The speaker will be Sean Andrews, astrophysicist at the Harvard-Smithsonian Center for Astrophysics. He will be speaking on the current understandings of the processes of planet formation, both around our sun and around other stars. The 2,452nd meeting and the President's lecture, tentatively, well, not tentatively, will be on January 14th in the new year 2022. Tentatively, the speaker will be Olivier Goyon, astronomer at the Stewart Observatory and professor at the University of Arizona. Olivier previously spoke about adaptive optics, but I wanted to hear a much more technical, mathematical, and physics-oriented discussion, and so I'm hoping that he will come back to give a fairly technical lecture on the scientific principles and technology and the engineering details of adaptive optics employed by large telescopes. The 2,453rd meeting will be on January 28th, 2022. The speaker will be Ray Lugo, CEO and principal investigator of the Center for the Advancement of Science in Space, the organization tasked with managing the U.S. national laboratory that is the International Space Station. He was previously the director of the Florida Space Institute at the University of Central Florida, and he will be discussing the ISS, science done on the ISS, and the future of the ISS, which I'm sure many of you have been reading about in the newspapers. And before you go, let's thank tonight's crew, our room manager, Laurel Kane, our check-in crew, Mark Clampin, Brett Magarum, and Cameo, well, Cameo's not here, our video and stream director and equipment boss and all-around person in charge of everything, Robin Taylor, our live chat coordinator and Rosette's person, Ann McQueen, the camera operators, Connor Nixon, Robert Thompson, Jared McQueen, and Noah Block. Our mic runners. Who are our mic runners? Brett Magarum, Robert Thompson, Ann McQueen. And our equipment handlers, Jared McQueen, Robert Thompson, Robin Taylor, and James Heelan for reading the minutes. Thank you all. And with that, I will now adjourn the 2,450th meeting of the Society. I wish everyone a good morning, afternoon, evening, or night, wherever you happen to be. The meeting is adjourned.